So hello everyone. Welcome to the second day of TezIndia Blockchain Bootcamp. I'm Swam Siddharth, your host for this evening, and today we will be doing consensus algorithm, proof of work, and proof of stake. So before we get into the session, I would like to request if you have doubts regarding the previous session. If you have any doubts regarding the previous session, please drop in the chat box. Ojasvi is here; he will help you regarding that. And if there are no doubts, please also comment that you don't have any doubts so that we can move ahead. I request everyone to tell whether they have any doubts or not. So I guess we can move ahead with the session today. So today we will be doing the consensus algorithm, then we will be doing the proof of work, then we will be doing proof of stake. So I would like to invite Ojasvi to the stage now so that he can continue with the session. Ojasvi, you can take it from here now.
Hey, welcome
Also,
back.
a little housekeeping. If you have any doubts regarding the session in between, drop them in the chat box. We will take those questions during the presentation. Also, we will be taking question at the end. Also, I would like to request everyone to please turn on their cameras to make the session a little more interactive. We have shifted from YouTube to Zoom today just for this so that we can make the session more interactive than yesterday.
Hey, so I'm audible, right? Okay, so um, all right. So let's begin with the second day. Uh, Yesterday we got to learn about many different things, but none of them were like completely into the blockchain. It was more like some topics that's needed to be covered before starting. So today is the actual starting. Today we are going to learn inside the blockchain that what actually happens, and this is where you will get to know many new things if you are not aware before that how does a blockchain work, then all of the stuff that you are going to learn today is completely new. So let's begin. So our first task is to understand what's happening inside the blockchain, and what are the things that we need to look at. So a simple block that that compromises in the blockchain looks like this. You have a kind of simple block of data. What is all of this data? We'll cover one by one. But this is how a block. Whenever you kind of try to visualize how a blockchain looks like, this is how it looks. This is a block, and it's covered to both of their neighbor blocks. This in the left you can imagine a previous block, and in the right you can imagine some other next block. Now inside this block we have some things. A very basic example, if you are making a very foundational level example of a blockchain, then you only need to cover these things. One is block number, that at which level this block is. The first block is called a genesis block, that is also called a zero block. And then you add more and more blocks and increment this number, which is called a block number. It basically tells you that how many blocks ahead are you. Then there's a nonce value. Now this is a very arbitrary value. It can be an integer, it can be a string, it can be anything, any kind of digital data, and it have its own purpose, which we will later cover. But for now, you can just remember that it's a normal value. Then we have all the data that we need to put inside. Now this data can be anything. In general purpose, like for the first example, if we take Bitcoin, this data was transactions, that who is sending how much Bitcoin to who. That is what the data was. So you can add any kind of data, whatever application you are making, whatever uh, use case you want your blockchain to be. So it depends on all of that stuff. But whatever kind of thing you want to store, this is the block where you need to store it. Now in this example, we are storing the transactions. So had coins are simple replacement to Bitcoins. And then we are just storing the transaction that Kirill sent 500 had coins to Hadlin. Kirill also sent 100 had coins to eBay, and Hadlin sent 70 had coins to Joe. So in a very basic example, like let's say Bitcoin, you only need to store these kinds of transactions, that who is sending how much money to who. And you can add multiple transactions in a single block and then add that block to the blockchain. The next part is called a previous hash. Now, this is what I covered yesterday, that whenever you have a block, in that block, there's a part where you need to store the previous hash of the block. So imagine a block number 2. You take all of the data, including the block number 2, the nonce of block 2, that all the data of block 2, the previous block that's stored inside the block 2, which is the hash of block 1, and the hash of that block. So all of that part is hashed together, and we get a small hash value, and we put that into block 3. So this is the function of it. You just hash the previous block and put that here. Now this green box is the whole block, and below that we see another hash, which is the hash of this one's block. So we hashed the third block and we got this value. Now this value will be stored in the fourth block. So this is how the blocks are connected. We take a block, we hash it, we store the hash value in the next block. Then we take that block, we hash it, take the hash value and put it in the next block. This is how it all connects one by one in a linear fashion. So these were the basic things that are included in the block. Now, so the block number, let's take a quick summary of it. The block number states the position of it, right? And the first block is called the Genesis block, which have a block number of 0. If you're starting your own chain, you need to have a Genesis block. And one thing that I'd like to cover is that the value of the previous hash in block number 0 does not exist, because I mean there is no block before the Genesis block. So how do you get the previous hash? So in that special case, we store 0 in the previous hash. So the previous hash value is all of the numbers are 0. It's like 0, 0, 0, 0. So that is the identity of a Genesis block, that it stores 0, 0, 0, 0 in the position of previous hash. Now, I mean, that's the convention, but if you like to make your own blockchain, you can put whatever you want, but we generally see 0. And so yeah, at the time I was making this PPT, block number 1943944 block was being added into the blockchain. So blockchain gets very big. It keeps on growing. So this block number keeps on growing too. And we have nonce. So nonce is always randomly generated. You cannot put your own nonce value that you want. Let's say I want to add 70 number on the nonce value. It might work, but it cannot work also. So you have to randomly decide the value of nonce, that what value you need to put. And so the process of finding the number nonce, the process of finding the nonce value is called mining in proof of work consensus protocol, it's called mining. So whenever you hear that Bitcoin is being mined, people are mining Bitcoin. This is what they are trying to do. They are trying to find a number that they can put in the place of nonce value for that specific block which is being mined. And we'll study that in the further slides too. So and we need to find it. We need to take a random value of nonce, put that in the block, try to generate a hash. If it works, that's good. That's the value that we will add. But if it doesn't work, then we again randomize the nonce value and check that repeatedly. And data. So you can put any kind of data in the data feed, and this data is generally transactions, money transactions in case of Bitcoin. But if we go to more generalized smart contract based blockchains, this transaction data is not just money, it's many things. And we will cover that when we get into the development part. But if I can show you the example data that we generally store in the blocks. So in case of Bitcoin, there are senders, there are receivers, and there's the amount, that how much Bitcoin is being transferred. And if you ever want to change the previous data, which have already being inserted in the block, then you cannot change it. Even if you want, you cannot change it. And we have seen that in the previous lecture. So let's show you the page where we can look into the blockchain. So we know, right, that the blockchain is always transparent. We can always look into the blockchain at what is being stored in it. So we can do the same thing with Bitcoins too. This is a blockchain explorer. So blockchain explorer is an application which general people can use to look inside the blockchain, to look at data that's inside the blockchain. So here is a blockchain explorer of Bitcoin, and can I hide this? Yeah, just a second. So yeah, look here. These are the latest blocks which were added into the blockchain. So these are the heights. Height is basically the number of block. So the latest block was mined 26 minutes ago. The mine is unknown, and the number is 732,869. And this is the size of the block, which means basically how much space is it covering on the node's memories, secondary memories. And this is the size of it. It's almost how much, 1.5 MBs or something. And we can view all the blocks here. So if we go to this page here, these are all the blocks, and here you can look the hashes of the block. So this is the hash. It's a very long string, so it's kind of trimmed from between. But this block was mined via BTC, and it's just mined. It's just literally just mined within 1 minute while I was speaking. So if we can look inside these blocks, we can click on the number, and this is the data inside the block. So there's a timestamp value also, that when exactly at what universal time this block was mined. And as like as a professional blockchain which is being running for so many time, there are many different fields which are being added. So there is a number which states how many transactions are we storing inside this block. Difficulty is something we will cover later. And version is protocol version, bits, weight, size, nonce. This is the value we were talking about. And below that, we can view all of the transactions that are stored in these blocks, in this single block. So we got a transaction from this guy to this guy. The person who was sending is Coinbase. So someone tried to withdraw some Bitcoins from Coinbase. And how much of Bitcoins did he withdraw? This much, 6.3727. This much Bitcoins were withdrawn from Coinbase. And this hash is basically um, the person, the address of the sender. This is the hash of Coinbase, and this is the hash of OP return. Someone is named OP return who have this address, and this is exactly how values the transactions are stored in the block. And we can also see the cases where someone uh, someone there's no name here, but some person with this address tried to, yeah, great. That was a thing that we needed in this session. Hey guys, host guys, can you clear it up? Alright, how do we clean this? I'm almost like I've become a college lecturer, I think. Your panel, I need the editor restrictions. Oh, I can also draw. Great. But I can clear it out also. Like this. Yep. Okay. But I know more than college teachers. You're not faster than me, boy. Can you clear out the permissions so that no one can draw post? Yeah, I can still draw. Okay, I think things are clear. Yeah, we got some questions. Let me just cover the questions. Meanwhile, Genesis block have any information in previous hash? Yeah, it's 000. I already covered that. Nonce is the block in the block differs from nonce that we get in MetaMask while signing a transaction. Yeah, that's a different one. How many links can a block have? It depends. It depends on the speed of blocks. So if many people are trying to make transactions, but you're really having some trouble to get the nonce value, then you need to add more and more transactions in the block. So that depends on the speed of it. That depends on the network, how fast is the network, and how active people are trying to make transactions. So it depends on all of the things, and that that adjusts the number of links that we can insert in the data part of the block. Is there any restriction on length of data? Yeah, there are sometimes restrictions also, and sometimes they are not. But it again, it depends on the speed of the block, right? You generally don't want the blocks to be much bigger, because it kind of slows the blockchain also, and it adds a sense of centralization too. So we generally avoid that, but we also avoid adding very less transactions to block, because then there will be more and more blocks and not much uh, data to play with. So we try to play in the middle, and we keep adjusting that according to the users. Yes, size of has limitation. What exactly is a blockchain? Oh boy, I think you are late. Uh, Blockchain is a kind of decentralized database combined with your backend part where you put the logic of the application. That's a very short but brief definition of blockchain. Can we again have an explanation of nonce? Okay, nonce will be covered in detail in the further slides. Blockchain is a database. It's the session. Yeah, the session have almost just started. Okay, so these are the transactions. We have covered that, and you can always go to this website and look more into the blockchain. You can even look inside the wallets also, like which guy is having how much bitcoins and other assets. For example, if I click on Coinbase, then this is the uh, data of Coinbase, that they got these much value transacted, right? And this was included in this block. So all kinds of um, data you can always look at. Why is there a restriction on data part of block? There's not always there's a restriction, but there's a cost of it. When you are trying to add more and more data, you need to give more and more storage fees. Now that fees is in terms of cryptocurrency, and the more data you are trying to occupy in the blockchain, the more fees you need to give. So that's why there's no restriction. I mean, you can give as much fees as you want, and you'll get to add more and more data. But I don't think you would like to lose that much amount of money. So we generally try to avoid only store the data which is necessary and not everything. Yeah, and fees is generally given so that less resources are used, including energy too. Okay, let's let's go ahead. So we have covered the previous block hash, which is we take the currently added block, we hash it, and we use that value in the next block, which we will add later. And and we also store the current block's hash. So the final block which we have generated, we also hash that, and that is also stored with the block besides it. So that's what we were looking at the website. There are some things to always remember, that the blocks are connected using hashes. You hash a block and take that hash value to the next uh, part of the block. And if you ever try to tamper the data that's inside a block, then that creates a problem. Because let's say you have a blockchain like this. This is block number one, this is block number two, and this is block number three. Now in this case, if you try to change the data part of block number two, let's say you change it like Coinbase was sending some coins to me, but not him. That means you're trying to tamper the data. And when you do that, other people can observe them. And how will they observe them? Other people can always hash the blocks. So they will hash the block, and the block hash will not match which is stored in the next block. So in this case, when the block was correct, the hash value was 6BQ1, right? So the block value was 6BQ1, and that was stored in the previous hash part of block 3. But when you change it, the hash value of this block will also change, because if you change the input of the hash function, you also change the output of the hash function. So you just change the input, you just change the data. Now when you have changed it, the hash is also changed. So the hash is now become uh, h62y, and that will not match with the previous hash of block 3. So you just um, tamper the data, and suddenly the hash values are not matching. So this is how cryptographically you can always very quickly validate that if the data of the block is correct or is tampered. And that is how we can maintain the integrity of it. So this is one one way we kind of maintain the integrity. There are many other ways also which we'll look further. Yeah, and also we discussed yesterday that the blockchain is maintained by a distributed P2p network. P2p here means peer-to-peer network, and a peer-to-peer network is like there are multiple computers which are called nodes, and these nodes are interconnected. So, for example, if I'm hosting a node on my laptop, then my laptop will be connected to many other people across the world. It can connect to someone in Nepal, someone in India, someone in Pakistan, someone in America and other parts of the world. So even in Antarctica, someone is hosting. So nodes are connected to each other in a uh, very clusterized uh, group, a single P2P network, and they all have the same copy of blockchain. So that also helps us to maintain the integrity, because if someone changes one block, tries to tamper a block, then other people which are connected to that person will also observe that. And this is a very simple way to analyze that. Okay, someone is trying to mess up the things, and that is how it's safe. And if someone wants to add a new block, we have already seen that they simply just append that block in the blockchain after they have completely validated that, and then sends that block or broadcast that block to other nodes, which then validates themselves that if the block is correct or not. And if it's validated, they also add the block and kind of spread that news to their friends also. So this is how a block is added. One person find the valid nonce, take that, adds it, and other people are uh, copying that if it's correct. And other people also verify it, and yeah, they keep sending it to their peers. So let's take a look at the diagrams also, so that you can visualize this procedure. The one block is added by this person, and the other people connected to this person will also validate that block, verifies the data and everything, that if the block is correct or not. And if it is, all of them adds it. Now, um, if in case there is a person who is trying to change the data, is basically trying to attack it, so that they kind of steal other people's money, and they have their own intentions. But if someone tries to attack it, uh, they need to change the part of the data which is somewhere in between of the blocks. And let's say in this case, this is the block which was being changed. And when they do that, all of the further blockchain also gets invalid. And the reason is when you change the data of the blockchain, the hash of it also changes, which doesn't match with the next block. Now, what the attacker can do is to match the hash in the next block, they can also change the next block, right? So, like in this example, um, this data was changed, so hash was changed to 6h62y. Now, this is not matching with the previous hash of the next block. So what they can do is they can also change the previous hash of third block. They will override this value with h62y. But when they do that, the hash of the third block will again change. So this value of 3h4q will also change. And the process repeats itself. I mean, from for to validate the second block, we change the third, but then to validate the third block, we need to change the fourth. But then we to validate the fourth block, we need to change the fifth. And this is how all of the further blocks are needed to be changed if you want your blockchain to be valid. And that is a very difficult task. I mean, adding a single block takes around, I mean, around half an hour in case of Bitcoin. So if you're trying to change some block in the middle, then you need hours and hours of work, combined power of the whole world to change the blockchain, to make it valid again, which is very difficult. If a single person is trying to change the blockchain, then most likely it will either get disconnected by its peers, because obviously he's trying to do some malicious things, um, or uh, he can also copy the correct copy of the blockchain from its peers and then replace it with the um, tampered blockchain. So it's up to this node. I mean, if it wants to disconnect, it can. If it wants to copy the correct snapshots of the blockchain, it can. So in this case, these are the connections which now knows these three nodes have observed that this node is doing something fishy. So these are this is the procedure when this node decides to stick to the plan, and they they basically copies the correct copy of the blockchain and saves it into their own memory of the blockchain. This is how an attack was uh, defended, um, and the blockchain's integrity is now maintained. So I think for now, how a blockchain looks like from inside should be clear pretty now. If you guys have any questions, you can keep them dropping. I'll just wait for a minute. Just a second. Keep dropping the questions.
So, Jashwi, shall we take some questions right now? Like, there are some questions in the chat box. Jashwi, am I audible?
Yeah. Yeah, you're audible. So I think there are no questions that good. All right then. Let's proceed with the consensus algorithms. Okay, how is appended block validated? Okay, so there are many things which we need um, to verify before appending the new block, and most of these verifications are cryptographic. So one of the verification is whenever someone makes a transaction, let's say I am sending one Bitcoin to my friend, then with that transaction I have to sign it. That signing is a digital signature process. So I digitally sign that transaction data, and I do it using my private key. So when I add that transaction into the block with the signature of the transaction which I generated, other people who will be verifying that block will also verify all of the transactions with the public key of the senders. So whoever was validate or verify that block, they will also take my address, take the public key of me from the address, and use my public key to verify the digital signature of that transaction, which will cryptographically prove that I was the one who made that transaction and there is no one else who is trying to mimic me. That's one thing that we generally see in many of the blockchains. I mean, in almost all of them, you need to have this simple validation procedure because it's actually very important. You need to check if the correct person is making the transaction. So that's one way. And there are many other ways also. We also check the nonce. That concept is just coming in the further slides. So these are the things.
Or just say there are some more questions. Will you take them now, or you would like to take them at the end of
Yeah,
the
yeah.
presentation?
Are they from the YouTube?
No, no, no. They are like around 7:30. There are some questions.
Okay, yeah, yeah. You can ask.
Okay. Okay. So Ashpreet Anand asks, Genesis block have any information about the previous hash?
It doesn't. It only has the 000 value in it. There's no information for a previous block because it doesn't exist. So we just generally place the zero values in there.
Okay. Prakhar Ojaid asking, nonce is the block differs from the nonce that we get in the MetaMask while signing a transaction.
Actually, these questions I covered in between
Okay. Okay. Then
previously.
let's just move on.
The latest question is new from Somil Agarwal that I'll just cover. What actually happens in the process of minting? Yeah, this is exactly we are going to cover in the further some minutes. In the further slides, we look at the consensus algorithm, and the first algorithm that we need to look is proof of work, and that includes mining. So we are just going to start with the mining procedure now. Okay, so let's just take a quick introduction to consensus algorithm. What are consensus algorithms? A consensus algorithm is a set of uh, set of steps or a complete procedure which all the nodes follow, and all the nodes doesn't actively have to do anything. It's just written the code, whatever client code you are using to host the node. The code is itself running in it, and it will follow all the procedures automatically. And this algorithm is needed for the complete working of the blockchain. This algorithms includes all of the validation process, like if a block is valid or not, should we add it or should we reject it, and mining also comes into its picture, and it also try to um, make a conclusion or a consensus if multiple blocks are being added at the same time, then what order do we need to follow for the blocks, uh, and we also generally see that multiple chains are being generated. So this is something which we generally see, and consensus protocols are responsible to let it not happen. Okay, um, I'll just I'll share you that in the next slides about the multiple chains. Yeah, we have that. So I'll explain that in the coming part. And every blockchain have its own consensus algorithm. Um, but mostly we see proof of work and proof of stake. And sometimes there are small changes in these algorithms only. So they are given their own name as a derivative. For example, Tezos use liquid proof of stake algorithm, which is almost the same as proof of stake, just some differences. And the nodes may not trust each other because they don't know each other. I mean, I don't know to who to whom node am I connected to in the world, so I cannot trust that person. But if everyone is following the consensus protocol, then there's no need to trust anyone. The blockchain will run on itself, and the procedure which is defined will hold the blockchain intact. And this protocol is generally a very large set of steps. So these are the steps for Bitcoin. I mean, it's actually very detailed, and it's a subject in itself. So, uh, and in the basic uh, part, we only just need to know only few things which we'll cover. So, coming to proof of work includes mining, which is also uh, known as cryptographic puzzles. Like if you try to understand it from different sources, from some YouTube videos or somewhere, they generally refer it to a cryptographic puzzle, refer the name as cryptographic puzzles. So that is one of its name. It's responsible to save us from attacks. There are mempools, which we will see. There are mining pools, and there are nonce ranges. All of this stuff we are going to cover. So first of all, let's try to understand mining. So the process is you need to find a way so that adding a block should take some time or should take some work. That is the intuition. You want that if a node is trying to add a block, then that node should do a lot of work for that, and that a lot of work will take time. So this is the intuition which we um, try to remember. So how do we do that? We have stated a rule in the consensus protocol, proof of work consensus protocol, that you need to include a nonce value, and when you include this nonce value in it, it will be added along with all of the other data, and then you hash that block. Then you when you hash that block, you get a hash value, and what we add as a rule is that this value of hash should be less than some limit. So let's say the hash value is again a hexadecimal number. It's a simple number just in hexadecimal base. Generally, we see the numbers of decimal base 10, but hash value is a number with base 16. So when we have this hash value, we state the rule that this hash value will be less than some number. And when a hash value is less, you will see zeros ahead of it. For example, 0045 is a number, and then we see 0004 a number. So which number is smaller? Obviously 0004. So we can um, kind of understand this, that if a hash value have large number of zeros ahead of it, that means that hash value is small. And if, let's say, there is no zeros ahead in the more significant parts of the number, then it's not much small. So what rule we state is that this hash value will have some number of zeros ahead of it. So here in this case, we we have a target of 4 zeros, which means whenever you will hash the block, that hash should have the should have 4 zeros ahead of it. Okay, should have 4 zeros in the most significant part of the number. Most significant 4 digits of this hash number will be zeros. And once we state that rule, things get very difficult, because again, hash value is always kind of um, random. We have seen the avalanche effect, that hash value is so much randomized that even if you change just one part of the input, the value becomes completely different. And so it's very difficult to predict that what kind of block will generate a hash value which will fall in this part. Now this diagram basically shows that all the possible hashes uh, are included in this box. And the more below you go, the more smaller hashes you will see. So the lowest line of this diagram is the smallest hash, which is 00000, and the highest line of this block is the largest hash, SH256 hash, which will be FFFFF, because it's hexadecimal. So the last uh, the last digit of a hexadecimal number is F. And what we generally kind of visualize here is that whatever hash value of the block you are getting, it should be under this target line. And the target is that the initial most significant values of most significant digits of this hash value will be four, 4 zeros. So now just one thing we have to repeatedly do is that we change the value of nonce. And once we change the value of nonce, we are basically trying to change some internal data of this block. And if you change the value of nonce, the input of the hash function will also change, which means a new hash value will be generated. For example, here we have stated nonce value of 177, which was randomly decided. We just take a random value, 177, okay. We place that 177 value here, we hash that block, and we get the hash value. Now this hash value we check if it falls under this line. Well, for this number, it's not coming under the line. So we again randomize the nonce value. Let's say we set it to 15. We set it to 15. The hash of the block again changes, and it again comes somewhere above the line. So we keep on doing this. We keep on randomizing the nonce, and then hashing, and then checking. It doesn't come. Then we again randomize the nonce. We hash it. We check the value of hash, and it doesn't come. We keep on doing this. We keep iterating the same, repeating the same thing again and again until finally we see a nonce. Let's say in this case it's 5012, which was when hashed. We saw 4 zeros ahead of the hash, and this means that a correct hash has finally been found, and this was only possible because of this value of the nonce. So when you find this kind of nonce and we hash that and we find a correct hash, that means we finally found a good nonce. And when this hash is generated, this basically means that finally this block is um, valid to append into the blockchain. Any block you are trying to append into the blockchain should have a hash which falls under this category, which comes under the target subset. So in this example, only the blocks which have a hash uh, way less than other hashes, and that hash should have 4 zeros ahead of it. Only those blocks are eligible to be appended into the blockchain. Now, why do we do all of this? I mean, what's the point of making it so complicated? The point is, when you follow this procedure, one thing which is always made sure is that when nodes are trying to add the blocks, they are doing a lot of work. They are again randomizing the nonce, hashing it, checking that. Again randomizing, hashing it, checking it. So for minutes and minutes, these nodes are always doing the same thing, which is called mining. The nodes just keep on randomizing the nodes and hash them and check them. And once in a um, very small probability, someone in the world finds that nonce, some node in the world finds that nonce, which finally gives us a valid hash, and that that nonce is called the winning nonce. Finally, some node across thousands and ten thousands of the nodes in this world finds this nonce, and they basically win. So that person is finally eligible to add this block into the blockchain, and now other blocks won't will not like will not need to repeat the same process. They basically know the nonce now. So some guy found this nonce value of 5012, and other people can now simply look at that value. Okay, so this guy found 5012 nonce. Let me add this number into the block we are trying to generate. They add it, and they also just hash it and check that you are right. The hash is coming fine. And that is how it's very fast to validate the blocks. Finding the nonce takes a lot of time. That's why adding a block is also very time consuming process. But when we come to the validation part, where everyone needs to validate the block that if it's correct, that's very fast. You already know the nonce. You just hash it and check that, okay, this hash is coming into the range. That means the block is valid. So when copying the block is the part, then that happens very fast. But generating a block is a very time-consuming process, and that is called mining. So in Bitcoin also, when we talk about Bitcoin mining, this is what they are generally doing. They keep on hashing. It needs a lot of computing power to do that. I mean, there are thousands and thousands of nodes around the world having tons and tons of terawatts of energy, and all they do is just randomize the number of nonce and hash it. That's all they keep doing. So you can already imagine how less probability does this have to comes under the range. This difficulty level that you are looking at is way more exaggerated. This line is almost just touching the bottom line. It's that much difficult. And uh, when we follow all of this, it's very easy to save it from attacks, because if someone is attacking that we saw here, they need to change the hash of this block and the next block and the next block and all of the further blockchain. So if adding a new block just takes so many minutes for the complete world, then a single person who is trying to hack the blockchain will take eternity to find some correct value of hash, even for a single block. So it will become very, very impossible for a single person to hack the complete blockchain, even the uh, uh, further part of the chain. And even let's suppose that someone is that much powerful using maybe quantum computers or something, that they are hashing it too fast, then maybe it's possible that okay, they completely validated the whole blockchain, but then they need to deal with the other people. Now even if this guy have a complete blockchain, other guy will look at that blockchain. They'll think at once that okay, this guy is also having a correct blockchain, but what about others? So the majority of the nodes will have the correct version of the blockchain, which means again this guy uh, either gets disconnected or they just copy it, uh, copy it from the other nodes. So it's almost like, probabilistically speaking, it's impossible to attack a blockchain which is adopted by the complete world. You're basically fighting the whole world using your network. Now let's look at the case where we see two nodes mining different blocks. So what does that mean? Let's say this person, this node right here, adds a new block. He found a nonce, that nonce was correct, and he just adds that block into their blockchain and broadcasts that node to its neighbors. But let's say there is some other node also, let's say it's this one, which mines some other block, and that block is having a different value of nonce and maybe having some other different transactions. So we basically saw two blocks at different nodes, and both of those blocks are cryptographically valid. But that creates a confusion that which block to accept and which block to reject. So this this confusion happens this way. Other nodes also copies this block, but then they will be having this confusion with these two nodes. So these four nodes will have confusion with these two nodes, that whose block should be accepted. And the way we generally resolve that is we we just wait. So until this significant part of time, the nodes are um, forming a kind of team. These two nodes are having its own node, and they are assuming that this node is correct and everyone is copying it. And these four nodes are also doing the same thing with their own node, with their own block. They are also having their own block. They are assuming that everyone is copying that, and everything is working fine. They just simply wait and keep on doing what they are doing. And then while this waiting is happening, another block is mined. So we generally wait for the next block to mine. Now, when the next block is mined, that block is mined someone from this team, the larger team. And when they found a new block, they add that block also into their blockchain. And now things get different. Now, this team is having a longer chain than this one. Let's say this chain is having how much blocks? 1, 2, 3, 4, 5, 6, 7, 8, 9. This chain is having 9 blocks, but this chain is having 10 blocks, which means this one is longer. So once we just arrive at this scenario, the other team have no other choice left, just just to discard this block and then um, copy others' larger blockchain to their blockchain. So finally, these 2 blocks will be copied to this one, and the purple block, which was also valid, will be discarded. And these discarded blocks are generally uh, termed as orphan blocks. They are valid, but they were never included in the blockchain. So, so this is how the case is covered when you got multiple correct blocks at different positions. So this is how it's being added. The orange blocks were taken from here and then they were copied here, and the purple blocks are kind of discontinued. They are still valid, but they are discontinued. And yeah, how an addition takes place. Someone adds a block, other people copies that. As simple as that. Just a second. We have looked at the definition also. Okay, now let's talk about mempools. Hmm. Now here you need to visualize a little. Um, Blocks have a uh, have a space for data where we generally store transactions. And what happens in the real world is that there are nodes across the world and there are general public across the world. And the general people uh, don't host the node. They just want to make transaction. So let's say I am someone who is one of the general public. I'm not hosting any kind of node or something. I just want to transact my Bitcoin values. So I just want to send 1 Bitcoin to my friend. So what do? I just make a transaction. I I just write it that I am sending 1 Bitcoin from my wallet address, their wallet address. I sign that. All of that happens automatically using some wallet, and I send that transaction to some node. Now, when I do that, uh, the transaction is not right away included in the block. That doesn't happen. And the reason is there are so many people who always wants their transactions to be added into the blockchain. But the blocks are not mined that quick. The addition of blocks takes about half an hour. So, so it's very difficult, right? Because if I have so many people who are trying to send transactions to the block, and the block can only have some megabytes of data only, then you need some kind of caching space, some sort of list where the unadded transactions will be stored, right? And that is called a mempool. A mempool is basically a place where your transactions are stored until it's not added in the blockchain. So whenever you make a transaction, the first place that your transaction goes is a mempool. Mempool looks like this. It's a simple list of all the transactions. And when a node is trying to mine a block, they take um, the transaction out of these mempools, put that in the blockchain, and then mine it. And once the block is successfully mined and added in the blockchain, then these transactions from the mempools are deleted. So if you made a transaction, let's say I got the first transaction is mine. So when I make it, that's added in the mempool. Some other transactions are taken in the blockchain. My transaction is still waiting, but at some point in the future, this transaction will also be included in the block. So whenever you are making a transaction with a blockchain, make sure that it's added in a block. It's not just stuck in the bank. And also make sure that you kind of wait uh, for some other blocks to be added, because it might happen that your transaction was added in a block, but then that block was just discontinued or orphaned. So make sure that whenever you make a transaction, you wait for some other further blocks which are added after your block. Okay, so that you can kind of have that sense of confidence that okay, now this chain will not be discontinued. Then we can also look at mining pools. So what are mining pools? Sometimes when uh, we generally see this in case of Bitcoin network, that when there are a lot of nodes, each node have its own computing power. Like if I'm trying to, let's say, host a node from a mobile, and then there are people who are hosting large and large of warehouses to do the same thing, which is mining the Bitcoins, then obviously it's very difficult for my mobile phone to just compete with large warehouses. So it kind of it's very impractical to compete with them. So what generally happens is that these nodes form a small group amongst each other and combine their own hashing power to compete with the warehouses. So in this case, what we are looking at, we got two groups of the nodes which have less power, but they combine their own power and then mine a single block using all of the power they have, and that somehow gets equivalent to the power of warehouse. So that way things aren't centralized. Because if in case the mempool was not forming, you will you will almost all of the time you will see that only the warehouses get to mine the next block, which makes it very centralized because the power is just at a single place, and we don't want that. So this is the way we kind of reduce centralization. You have multiple nodes making a team and then using their own combined hash rate or hash power to compete with other warehouses. So this is how equality is maintained between almost all of the people. And all of these things are automatic. It's just stated in the consensus protocol. You can look at the mining pools here. Like in case of Bitcoin, this pie chart shows us the mining pool. So there is one mining pool, which is the largest one, is called Ant pool. And then at the second place, we got F2 pool. Then we got YBTC, which we just saw someone mined a block, and that was via this, that was from this mining pool called YBTC. Then we got a pooling pool, slush pool, SPI crypto, and these are all the unknown people. These are not forming any kind of pool or something. They are just working on their own. And one thing I would like to point is that having mine pools is not beneficial. Forming mining pools makes it centralized, because let's say if the top 4 or 5 of the mining pools of Bitcoin forms a team with like a team of team, then more than 50% of the power of the blockchain will be with a single organization, and that will create centralized system. So generally mining pools are avoided with the blockchains. Now let's look at the nonce ranges. So what happens with mining pools, that how do they combine it? They do that using ranges. So what are nonces? Nonces are random numbers, and that number can be anything. Let's say that number can be from 1 to 1000. Okay, so when we form a mining pool, we kind of allocate the ranges of the nonce to multiple nodes. So in this case, we formed a mining pool with 5 people, and we will say that this guy will find the nonce the no, will basically mine the block within the nonce range of 1 to 200. This will work within the nonce range of 201 to 400. This one will find the nonce range between find the nonce between the range of 401 to 600. This one from 601 to 800, and this one from 801 to 1000. So this is how you basically divide the ranges of the possible value of nonces and allocates that range to different people, so that no two nodes are finding within the same uh, within the same range, and that will increase the probability of finding the nodes, and that will also make that will also help us to make sure that they are not competing with each other. I mean, if all of them are still finding the nodes between 1 to 1000, then obviously there's no point of forming a team. But if they divide this nonce range in this fashion, they're kind of doing a divide and rule kind of concept. So this is how nonce ranges are used to find the final uh, valid block. So that was proof of work. If you have any questions with proof of work, uh, you can drop them, and then we'll go to proof of stake. Proof of stake is not that large to explain, so it won't take much time. Okay, I think let's just cover the proof of stake also, and then we'll wait for questions. So let's talk about proof of stake. Now, proof of stake is obviously a whole new different algorithm, and this consensus protocol was made because proof of work had um, some caveats. There were many disadvantages of using proof of work, and one of them was the usage of power, usage of electricity. I mean, there are people running warehouses at different places to mine bitcoins, and if we just talk about how much power does it take to run bitcoin, that combined power that all of the miners use is very comparable to countries, and I think it falls between uh, some two countries. I think Argentina and Switzerland, or maybe Argentina or UK. It comes under these countries. Okay, it comes in between of these countries. So that much, that's the idea of the power that the whole network is taking just to find nonsense. And there's one way to avoid that. I mean, this is why also people avoid proof of work because it increases the carbon footprint of it. So Bitcoin carbon footprint is very, very, very high, and we definitely don't want that. So that's why proof of stake blockchain are much preferred because it doesn't it helps us to um, make it more economical and eco-friendly too. So here blocks are not mined, they are forged or minted. So that's the term that we generally used for generating a new block. And there are no miners in the protocol, they are validators only. And we got no kind of cryptographic puzzles that we need to find the nodes and hash it. That's that's not needed here. So power is not wasted, and this is how the proof of stake looks like. So uh, when you need to introduce yourself in the network as a node, you just don't go there and say, okay, I'm a node, let's connect to it. That's not going to happen with proof of stake. In proof of stake, you need to send some cryptocurrency into the network as a stake. So you need to take your money, some part of your money, and then deposit that money in the network as some kind of a collateral. Okay, and that money is locked in there. Now, when you lock your money in the network, you cannot take it back until and unless the network allows you to. So now your money is locked into the network, and once you lock it, then you become the part of the network. Now you are the node, and now when we need to add a new block, a random node is selected from across the network, and it the the probability of you being chosen as the node depends on how much money you have deposited. So if you have deposited a, a lot of money as compared to other nodes, then you will have a greater probability to be selected. Now, why do we get selected? We get selected because the selected node needs to just basically make a new block. When you are selected, you get the opportunity to take all the transactions from the mempool, put it into a block, validate all the transactions, validate the complete block, and then that's it. That is the process of forging the new block. You have just created a block, and then you say to other nodes that, okay, I was giving the responsibility to make this new block, and I made it. I'm adding it to the network, and you guys can validate. And then other people in the node validates that block, that okay, if this generated block is correct or not. And if it's correct, all of us adds that into the blockchain. But if in case that block was found malicious, you tried to do something wrong or something, you basically try to tamper the block or create an invalid block, then uh, the network decides to take your deposited money, and you will never get that back. So that was the point of depositing the money. You were given a responsibility, and you didn't forged a valid block when you were given the chance. And since you were trying to um, create a false network, your money, some part of your money is taken, and that taken money is given to the person who will identify that you forged a wrong block. So that's the incentive for others to check if your block was correct or not. So it's a kind of a um, a civilized fight between the nodes, that whether whether people are doing what they are responsible to do or not. If you are the one who is minting the block, you need to mint it correctly. If you have minted it correctly, you will be given the incentive for that, some cryptocurrency, that okay, you have done the correct work. And if you didn't do that, if you were given the opportunity and you uh, use that use that opportunity to make some malicious block, then some part of your deposited money will be taken, and and also you will not be given any incentive to work, and that all of that money which is taken from you will be given to the person who identified that okay, you were doing something wrong. So if in case someone else is uh, forging a new block, then you need to check that if they are doing it correctly or not. Because if in case you find that this guy was doing wrong things, then you will get the deposited money which they deposited. So this that is how this rules set of rules are um, responsible for the blockchain to run. This diagram will help you to understand that you got multiple validators. This is the blockchain um, which is running. This is the uh, newly forged block. So this is the validator who stakes some coins, and the amount of coins you are staking can be different. It's up to you how much amount of coins you need to stake, but there's always a lower limit that you cannot stake less than this. For example, I don't remember for Tezos, it's I think probably 1000 Tez or something. That's the amount of money you need to stake. And once you stake it, you become the part of the network. Now, this validator was given the responsibility to add a new block. It adds that, and then other people will validate. So that was proof of stake. Now we can look at liquid proof of stake. It's very similar. The only differences are that validators here are called bakers. The name is changed for it. And the validated block is not broadcasted to everyone. It's just broadcasted to other 32 selected nodes. So whenever the nodes are selected, 33 nodes are selected. One is selected to basically mint the block, and the other 32 nodes are responsible to validate it. And those 32 nodes, if they approve the newly created block, then that block is good enough to be added into the blockchain. The baker who minted that block is rewarded, obviously, and other people who were testing it also gets rewarded because they are also doing some work. And if in case the block which is just created is not valid, then the person who uh, who, who observed that, who took that into the notice, they get their they get the same deposited stake. And the block is rejected. That block obviously is not going to be added into blockchain. And one more thing, there is a process of delegation. So delegation basically means that sometimes you don't have enough resources to become the part of the network. By resources, I mean money. Like in case of Tezos, if you need 1000 Tez to become the part of the network, and one test basically means $4 or $5. It's kind of um, very expensive. So mostly what you can do is you make yourself available to uh, to take others people money. So let's say you have your own friends, let's say 10 or 15 friends. All of your friends will give their money, their part of money to you. You will accumulate all of the friends' money to yourself. Um, Now finally you have more than 1,000 tests, and now you are participating in the network. And whenever you will get any reward for being the correct node, that reward is distributed amongst your friends. So, and that's also proportional. If if let's say um, a friend of you is contributing almost 90% of the stake, then they will get 90% of the reward too. So, so that is called delegation, which means your friends are delegating their coins to you. You are participating as a baker um, in the network. So this way, more and more people can participate in the blockchain, and it does not limit you to to not be the part of the blockchain. Okay, to be the part of the blockchain. It does not limit you. And one more thing is that um, they do not have to share their ownership right or lock their tokens. Yeah. Uh, Whenever you're staking in a normal proof of work consensus protocol, whenever you are staking your coins, even after you have mined the block, you are not permitted to just quickly withdraw your funds. That's a kind of uh, a, an unsecure way, because let's suppose you added a new block, and that then you made a new block, you took your money back, and that block is offered. That basically means your work was not um, used in the blockchain, and you still get the reward. So that's not good. So to avoid that, um, in proof of stake blockchains, not liquid proof of stake, but proof of stake blockchain, whenever you deposit some coins, there is a timeout for how much time you need to wait before withdrawing your coins back. But in uh, uh, liquid proof of work, that's not the case. Liquid proof of work is designed in such a way that it's even secure, even if you take your uh, take your money back. So in the process of minting and adding to blockchain while others are working, your tokens are liquid. They are not completely locked. You can take them back too. But then again, if you take it back, you won't get the reward. That's the way. That's the part. So this is how liquid proof of stake name is given to it. There are also other variants of this liquid proof of stake. So we won't go into that much depth, because there are so many variants, and even the proof of stake is kind of a variant. So this is how it looks like. These are the people who um, who delegates their coins to a single baker. This baker will take the transaction and uh, forge a new block. This block will be validated by 32 other bakers, uh, and they will either endorse it or accuse it. Endorsing a, is a fancy name for saying that the block is good enough, and accusing basically means that the block is not good, it's invalid. So these 32 people do that, and if the block is valid, then it's added into the blockchain. And finally, after adding the block, the rewards are given to the baker and the 32 people and the people who are delegating their coins to the baker and 32 endorsers. So this is a system which is called liquid proof of stake consensus protocol. So that's it. Today you learn a lot of things. Any doubts? If you guys have any doubts, you can ask them in the comments in the chat. What's the meaning of forging or minting? It's just a name given to the process of making a new block. In case of Bitcoin, mining is the process where you do all the cryptographic puzzle stuff, and in proof of stake and liquid proof of stake, you have the name of forging or minting, which basically means that you are making a new block. That's all. There's no special in it. It's just a fancy name for making. That's the meaning. How does a block is verified that whether it's valid or invalid in liquid proof of stake? It's almost the same as proof of stake. There's not much different. Solana is proof of, no, I think Solana uses some other consensus protocol. It's I think it's proof of history. It's either proof of history or proof of future. I'm a little confused. I don't remember. I'm pretty sure it's proof of history. Let me just quickly Google that. Let's see if my guess is correct. Yeah, consensus protocol. Yeah, proof of history. Any more questions? Yes. Any kind of confusion or doubt? Today's session was quite informative. If there are no questions, then I think we can move ahead. Is finding nodes will be the job for minting in POS? No. In proof of stake, there's no finding nonce sort of thing. That's not needed in proof of stake. It's only in proof of work. And that was the reason for switching to proof of stake. But it's not included in it. How the block would look like in proof of stake. Um, Let me show you that. Let's open the block explorer of Tezos. So one of the most popular one is TZKT. Also, proof of stake blockchains are quite fast, not as slow as proof of work blockchains like Bitcoin. So this is the Tezos blockchain explorer, and you can look at these bakers adding the blocks. The latest block was added uh, at 7:14 Universal Time, and yeah, we just saw a new block being added. So if we look inside the block, this is the block number 2300162, the latest block that has just been added, and this is how it looks like. These are the transactions. So someone sent 2000 tests to someone called a smart contract function with this much amount, someone transferred, someone sent, someone called. These are the transactions, and this is the number inside it. So you can go to this website and explore that what are all the data which we store inside the block. Timestamp, cycle, cycle is sort of asking treasures. Payload proposer is the person who proposed the idea that okay, these are the transactions that we should include in the blockchain. And we got a block producer, which means who actually baked it, made it. Software is uh, just a version that what version of the code is being used. This much endorsements were given. This was the reward, which means uh, this much amount of reward was given to the baker, the 32 people, and the delegators. Right. Gas is something we'll cover with smart contracts. Storage is how much storage was this whole block is occupying. Yeah, this is the data. So it's pretty similar to a general blockchain uh, basics, like basic structure that I just showed to you today. And every blockchain have its own kind of structure. So this is the Tezos. There are other blockchains too. Maybe Solana have its own structure. So it differs from blockchain to blockchain. Any other questions, guys? Validation by others in proof of stake means repeating the whole process done by Baker. Not always. Baker does many other things too, which validators doesn't have to do. For example, deciding what transactions do we need to put in the block. That's something which validators don't care much, but bakers need to decide. And there are some other things. Not the whole procedure is not same, so that's why the baker have to do more work than just validating. Prerequisite for blockchain development. Uh, for block, like if you're starting with blockchain, almost kind of have some experience with general web development. Uh, it's recommended to just kind of learn web 1 and web 2 stuff before getting started with web 3, because web 3 applications and projects are generally developed with along with web 2 um, frameworks. So you need to know basic web development for that, and rest of the stuff is just some theoretical cryptographic things which we covered yesterday, and that's it. If you know web 2 enough, you can always start with web 3. There's not much extra. And before developing any blockchain application, use it first. Like don't just completely start with blockchain development. Try to use some of the mm, basic web application, web 3 applications like an NFT marketplace or some market predictor. These are the sort of small projects. If you get to interact with that, you'll have a basic understanding of how to use wallets, how to make transactions, and that will be enough to get you started with blockchain development. Shall we close the sessions if there are no more doubts? The quiz today. Yeah, that will be covered.
Yeah, Somil, there is a quiz today. It will start after some time.
Can you explain how digital signature is used for example? I explained it yesterday also, and I explained that today also. Uh, it's a very simple process. It's just you take a normal data, whatever you want to sign, you hash it, and then you encrypt the hash using your private key, and that is the signature. Now, whenever someone need to uh, validate your signature or verify your signature, they take that encrypted data, they decrypt it using your public key, and whatever decrypted text you get, you compare it with the hash of the data. So again, you generate a hash of the original data and compare it with the hash that you got from the signature. And if both the hashes are equal, that is that basically means that it's valid. That is the procedure of verifying. So it's used in the places where you need to make sure that the data, whatever you are looking at, is actually generated by the sender and no one else.
So, Ojasvi, shall we move to the quiz now?
Yeah, we can if there are questions.
Yeah,
Yeah,
let's just start the quiz. So, I'm just sharing the direct link for the quiz. Here is the quiz now. So I guess all the participants have joined. So all the best to everyone. Let's see who is today's quiz. So 15 out of 19 participants have completed their quiz. Himanshu is now leading the vote. Let's see if anyone can take him over. Let's just wait for a few more minutes and then we will end the quiz. Two participants are still remaining to answer all the questions. So here we come to the end of today's quiz, and all kudos to Himanshu Kushwa for acing today's quiz. Then it comes to Mayank Panda and followed by securing the third position by. So with that, we come to the end of today's session. We all will see you tomorrow. Tomorrow we are going to start smart application and dApps. So thank you everyone for joining today. See you tomorrow. Good night, everyone.